Basics of C. We left off starting to talk about operators last time, where we had the basic addition, subtraction, multiplication, and division operators, and we'll get some more practice with that today. Remember that we are online, so if you have any questions, go ahead and post to Piazza or to the YouTube live stream, or just raise your hand in here. But otherwise, those are pretty straightforward, and we'll talk about them in a little bit more detail in a second here. But another operator that you're somewhat familiar with already because I've implicitly used it here is the assignment operator. It is a single equal sign. Right? So this is not algebra, right? It is not an assertion that the left-hand side is equal to the right-hand side, and that is either true or false. A is equal to B plus 5 or something like that, right? What it is it is a directive to take the thing on the right-hand side and put it into the variable on the left-hand side. And we've used that down here, right? When we computed the kilometers. We computed kilometers per mile times miles, and then we put it into the variable KMS. We took the result of the expression on the right-hand side, and we put it into the variable on the left-hand side. In other words, the thing on the left-hand side always needs to be a single variable because that's the target variable that you're putting stuff into. The thing on the right-hand side can be a value, what we call those literals, or an expression like this, A times B, or even more complex expression. If you put, say, kilometers plus 5 on the left-hand side, that is not something that is compilable, right? The compiler will now complain about this. That looks like algebra, but again, it's coding. It's not algebra, right? So it's a single equal sign. And again, it takes the value on the right-hand side and places it into the variable on the left-hand side. So in other words, the left-hand side has to be a variable. Now, what if I did some expression like, say, I don't know, let's expand this out, and let me go ahead and create a new copy, miles to kilometers to demo. I just need some a demo code over here. And let's go ahead and get rid of, well, let's get rid of this stuff, and get rid of this. And we'll start clean with a nice clean program here, all right? Let me go ahead and create some variables. A is equal to 10. Int b is equal to 20, right? And what am I doing there? I am creating these variables and immediately assigning them. Int c is equal, I'll leave it like that, right? So if I were to print these out, printf, a, b, c is equal to %d, comma, %d, comma, %d, right? And I'll end the line, a, b, and c. Right? Now if I were to print these out, then clearly A would have a value of 10, B would have a value of 20. What value does C have? Nothing. Nothing? All right, what's nothing? And you'll find in C and in coding, there's lots of different concepts of nothing, right? There's void, there's eventually null, there's the null terminating character, there's zero, right? So there's also lots of these concepts of nothingness. What do we mean by nothingness here in this context, though? What value will it print out? Zero? Okay. Yes, it did. But that is because of this particular compiler, this particular system. If you just look at line 9, the C standard does not say what is in that variable at all. It was my compiler putting in 0 for me, right, and saving me from myself. It could be that there was garbage values in there. Whatever was stored in memory, that memory location, the last time that memory location was used. It could be something like, say, dead beef. X dead beef. Right? That's hex code. It's a little, it's a little joke, right? It's what words can you spell just using the letters A through F, right? Well, dead beef is one of those things. And it could be that it's uninitialized variable. If it's an uninitialized variable, that means that it could have a value of dead beef, right? Don't assume anything about what's in that variable. 9 times, or even 99 times out of 100, yes, it will be 0. It's that one time that there's a garbage dead beef value in there that will then end up with garbage values in your result, right? So, say what?
May or may not break your code.
It may or may not break your code. It is, in the C standard, it is called undefined behavior. And when you have undefined behavior, it's player's choice, right? Whoever wrote the compiler, then they decided what happens. Yeah? If you want it to be 0, you should explicitly set it to 0. Absolutely. That's why you should always initialize your variables. And if you want to compactify this, b is equal to 20, c is equal to 0, all on one line. But leaving it just uninitialized, it's not a good thing. Right? We'll see this. We'll see the impact of this later on when we try to say add things up. If I've got an entire collection of elements and I want to add the first one, the third one, I want a second one. I want to add them all up. And if I start out with 0, it'll work. But if I start out with an uninitialized variable, it may or may not work, and I'll get some garbage values. So generally, you want to initialize your values, right? Well, you can also compute weird entire expressions, right? So let me go down here. I can reset a value. Right? I don't want c to be 0 anymore. I want it to be 30, right? So it was 0 when I initialized it. It was 0 when I printed it. And now it's been changed, and all the way down, unless it gets changed again, it will forever change, right? What if I do something like this? A is equal to c, and then I say that c is equal to 42 now. Predict what values will each one of these variables hold now on the second printf statement. What value does a have? Let's follow through. It had 10 before, right? On line 6. We come down and set c to be 30. We then, on line 12, set a to be equal to c. What value was c stored in c? 30. And I don't have enough fingers here to express it, so 30, right? Now what and then we change c to 42. Does a get changed to 42? No. It stays the same. It stays the same, and we end up with, altogether now, 30, 20, because we never touched that, and then 42. Save that, run it, and run it again. 30, 20, and 42. Right? Saying that one variable is equal to another variable simply takes the value in that variable, copies it over to that other variable. It doesn't inextricably link these two variables together forever. Right? It's simply taking the value on the right-hand side and giving it to the variable on the on the left-hand side. You can also have full expressions here. So, I don't know, double r is equal to b times b minus, how do I do a square root? SQRT of 4 times a times c, all divided by 2 times a. There we go. So what am I trying to do there? B squared minus 4 square root of 4ac. Oh, is that right? B squared minus negative b squared? Oh, okay. Actually, I'm trying to do, I don't know what I'm trying to do. Negative b plus minus, then what? Square root of 4ac all over. Yeah, it should be b squared here too, right? There we go. Thank you. All right. So what am I trying to do there? I'm trying to do the quadratic equation, right? Lots of mistakes, though, right? Now, normally, if you wanted to, first of all, plus and minus. Can I do something like that? No. That's not even correct math. That's not a function. It's just saying that there are two roots. Here's the first one, it's a plus. Here's the second one, it's a minus. You can't have a function mapping to two values. So let's choose one. I'll stick with the other. Well, let's go ahead and go with plus here. All right, there we go. Now, is that the correct math? Doesn't look right to me. If I were to write this out math-wise, I would have a numerator and then a big line and down below the denominator. This entire thing is the numerator on top. This entire thing is the denominator on the bottom, right? So what do I need to do to make sure that the order those operations are correct? Yeah.
Put every side of it in parentheses.
Parentheses there, parentheses there. Is that good enough? No. Nope. Because now what happens? I've got that, the numerator is correct, and then it's divided by 2, and then multiplied by a, right? Not correct. I need to put the entire denominator in parentheses as well. Why? There's this thing called what in math? There's an acronym for it. PEMDAS, right? Remind me, what does that stand for? Parentheses, right? Exponents. Don't worry about exponents because we're not going to use them yet. I'll show you how to do it in a second, but we don't have native exponents in C code. Then M is multiplication, then division, then addition, and subtraction. Same thing with code, right? That A times, or A plus B times C is not the same thing as if I put that plus in parentheses. Putting parentheses changes the priority of those operations, right? By putting something with a lower priority of operation in parentheses, it takes it all the way to the top because of the P in PEMDAS, right? So if you need to do something, and when in doubt, go ahead and put parentheses. Don't go overboard on the parentheses, but put enough parentheses in there to either make it readable or at least to make it correct, like I've done right here. Okay? I don't know, what's the root? R is equal to, now my placeholder for floating point numbers is not a D, what is it? If I want to print out R here instead. It is F. LF would be for scanf if I'm reading it in, okay? I don't know, what is, oops. All right. If I'm going to bring in the square root library, or square root, what do I need to bring in? The math library. And I might need something else. There you go. Undefined reference to square root. How do we square this away? Unfortunately, we may need to use -lm sometimes. Now, don't worry about what that means. If you want to know what it means, it's link in the math library. Link L, the math library M, right? And that should work, right? You'll have that issue in tomorrow's lab and certainly in Thursday's hack. Right? There's a reminder in the handouts. There we go. Nan. Why? What is Nan? Not a number, right? Some things can go wrong. What went wrong here? If you take out your calculators and compute, what is B? 20, 400, minus 4AC, 4 times 30 times, 30 times 42. That's going to be greater than 400. So in this radical right here, what do I have? A negative number. What's... Yeah, what's the wrong with, what is the square root of a negative number? It's imaginary. And imaginary numbers are not supported by native C code here. Right? Okay? So you do have some issues with those operations. Another one, let's look at another issue. I'm going to set A to be 0 and B to be 10. And then I want to compute their quotient, whatever it's called, A divided by B, right? So what is 0 divided by 10? 0, right? What if I switch them around? 10 divided by 0. Let's find out. C is equal to %D, and then we'll go ahead and do that. Nan? And then floating point exception, and it killed the entire program, actually. It didn't even print that out, right? Division by 0, it killed the entire program, right? To avoid something like that, I'm going to need conditionals, and that's the next module. So keep that in the back of your mind. Let me go ahead. So division by 0 is illegal, undefined. You could sometimes end up with inf. Inf is short for infinity, right? You could sometimes end up with negative infinity, right? Let me go ahead and set one more. A is equal to 10, B is equal to 20, and certainly double, I've already got R, so I'll go ahead and set that to be A divided by B. Remember that R was declared to be a double here, right? So 10 divided by 20, we all know what that is. What? 1/2, right? 0.5, right? Let's see if it actually comes out to be 0.5. Now, R here is a floating point number, so the placeholder is F for float. Let's recompile it. Oh, you know what? I'm gonna go ahead and get rid of this stuff so that it actually runs. There we go. Oh, cool. How did you do an entire block of code again? Comment out an entire block of code. Command or control, and then the /. Right? Goodbye, hello, goodbye, hello. Run that. All right, so you predicted that it would be 0.5. It in fact is 0. So you're learning all sorts of new math today, right? 10 divided by 20, it is actually 0. Right? Why? What's going on? So when you take an integer, 10, and another integer, and you add them together, you get 30, which is another integer. That's always true. Integer minus an integer will always be an integer, right? A whole number. Integer times an integer will always be a whole number, will always be an integer. For that reason, in most programming languages like this, an integer divided by an integer is also going to be an integer. So now think about this. 0.5. What is the integer part of that? 0. What happens to the 0.5? It gets chopped off and thrown away. That is known as truncation, right? So when you divide an integer by an integer, the result is always an integer. Right? The fractional part, that is the floating point part, is truncated. Right? It is cut off and thrown away. It is not rounded up. It is not rounded down. All right? There is no rounding in this entire process. It is cut off and thrown away entirely. Right? To avoid this, you can use typecasting. Right? So let me go back over here and fix this. What I'm going to do is I'm going to tell C, hey, for the purposes of this division, temporarily treat B as a double. Now, an integer divided by a double, that's going to be a double. A double divided by a double is going to be a double. You can go ahead and typecast both of them if you want to, but it's not necessary. Just at least one of those needs to be. The first one, the second one, it doesn't really matter. And if you do this typecast, oops, there we go, then you will get the right answer, 0.5 down there. All right? Now, did that change the variable b? Nope. It only changed it temporarily for the purposes of this division right here. It doesn't change its value. It doesn't change its type. B is still 20, and it is still an integer. It is not 20.0. It's only 20.0 as far as this is concerned right here. Right? So that is an explicit typecast. I'll make sure that you've got this as a code block, or in the notes here. Right? Any questions so far? Yeah. Strings in C are char stars, which we haven't got to yet because that's a pointer. A pointer is a memory location. A memory location is a long integer. And so if you typecast it, you'll get something, but you'll get memory address 7425 from your computer, which is completely meaningless to you because it's just a memory address sitting somewhere living in your computer that you have that you don't care about. You won't be able to do that. We'll talk about how to convert strings into numbers by the end of the day, though. All right. Other questions? Okay. PEMDAS rules. Let's see. What else? Truncation. Good. We already looked at overflow. Here's another operator. Integer division. So here's another operator that's kind of related to that truncation issue. You can use the integer division operator, which is a single percent sign. Right? So here's some examples. If I go with 10 divided by 3, So this is integer division. It actually gives you what's the remainder of this operation. So go back to grade school where you didn't know that you could go ahead and divide 1 divided by 3 is 0.333 or 1/3, right? And said everything is an integer. 10 divided by 3. 3 goes into 10 how many times? 3 times. What's left over? That's called the remainder. So if it goes into it 3 times, that's a total of 9. What's the remainder? 1. The result is 1. This is the remainder. Right? Some other examples. What if I go 10, and sometimes we read this as mod, if you've ever seen the modulo, it's short for modulo, but we'll just go ahead and say percent sign here. 2, right? 10 divided by 2. 2 goes into 10 5 times evenly. So what's the remainder? Results in 0. Excellent. What if I have, say, 11 mod 2? Results in 1. Why? It goes into it 5 times with a remainder of 1. What does that tell you about the usefulness of this operator? What can it tell you if you divide by 2? If it's even or odd. If it's even, the remainder will be 0. If it's odd, the remainder will be 1, and you can check for that when we get to conditionals starting Wednesday maybe. Right? Some other examples other than just modding out by 2. What about, say, 11 divided by 3? Results in 3 goes into 11 how many times? 3, with a remainder of 2. And 11 mod, or no, mod 11. Let's do that one. Results in 11 goes into 11 one time with a remainder of 0. Right? Okay. Yeah. Others? One more. 20 mod 11. There we go. Results in 11 goes into 21 time with a remainder of 9. Right? Okay. More math stuff. Right? So, again, you have this really, really nice math library that has several constants. M underscore pi, that gives you a representation of pi. Don't going and making your own pi. Use that one. It's way more accurate than you could ever hope to put out, right? You'd have to calculate it out to 17 decimal places, and even then, you don't know if that's the best precision that you can get on that system. Instead, the math library has taken care of that for you. M underscore E. E is 2.71 blah, 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 right? And those are 2 constants that you can use. You can also basically find anything that you would have on your graphing calculator or your scientific calculator. Sine, cosine, tangent, square root, pow. What do you think pow is short for? Power. What if I wanted to raise, say, a to the b? Let's go with a is equal to 3. Here, let's do, I'm going to go ahead and start over. Actually, I'll make sure that you have that in your notes at the end so we don't lose it. There we go. Everybody saw the Piazza post where I pointed you to all the notes on GitHub, right? Good. If no, then go to Piazza, right? It was the weekly retrospective that I post at the end of every week, a pre-weekly perspective at the beginning of every week. So let's go ahead and go double x is equal to, I don't know, 1.23. Double y is equal to 7.32, right? And I want to compute x raised to y, so double z. Now, some of you might have seen programming languages or conventions that do something like this. X raised to the y, right? That's a little caret that says, put that y up there because you can't write x and then as a superscript y, you can't write that in code. So what's the next closest thing? Well, this little caret that says, put that y up there. That doesn't work. It will work, it will compile, it will not give you what you want. That is the bitwise exclusive OR operator. Now forget that I said that, right? Because we don't want to do any bit twiddling in this course yet, right? Some of you might have seen programming languages that use the star as an exponent operator. Neither one of those works. You do have this nice pow function that raises x to the y and returns the value. Right? And printf z is equal to, I have no idea what this is, so you're going to have to pull out your own calculators and find out what is here, Wolfram alpha. 1.23732, 1.23 raised to the 7.32, 455 and change. Right, there we go. Right, 455 and change. Right. Note what I did there. I continue to use the -lm flag because I am doing stuff with the math library here. Right. Yeah, that's good for now. We'll revisit some more math library stuff later. Right. But otherwise, sine, cosine, tangent, etc. You also have, say, logarithms. Right. Now, log is the natural base e log. Right. If you need base 2 or base 10, you need to do conversions. Exp is e raised to whatever. You could use that pow function, right, and put in e raised to 2 or something like that, but it's so common that they just put it into another function, exp. Right? And finally, again, remember that you may need to compile using that -lm flag in order to link into the math library and get it done. Right? What else is there? What other nice functions might be in that library? How could I find out? Visit your local library, right? Your local library in 2022 is Google, right? We say read the manual, RTM, right? And if we really want to emphasize that, we say RTFM, right? That just simply means go out to Google. What's in the math library, Google? Right? See math library. Right? What might be there? And here we go. Tutorials Point's not the greatest website, but at least some stuff will be there. Ooh, arc sine, or arc cosine, right? Exp, LD exp, various other things. Ceil for the ceiling, floor for the floor, absolute value, fabs. Right. So what else is out there? Read the manual. In other words, just Google for it. Okay. It is always okay, in fact, highly encouraged to utilize what's built into the standard libraries already, right? Many people, are weary about that. Like, if I use a standard library function, am I cheating? No. That's exactly. Are you cheating in math when you hit your tangent button on your calculator? No, right? Absolutely, go ahead and use that. All right. Any questions so far? No? Then let's look at formatting output. Right. So recall that you can use printf to print to the standard output. Right. And there are placeholders. Right. %d for integers, %f for floating point numbers, and %c if you just have a single character. We'll have very little need to use that, but if you need to print out a single character, %c is what you use. You can also use modifiers. Right? You can specify the precision, right? The number, that is the number of significant figures to print. Right? By default, 6 for floating for double values. 6 digits of precision are printed. Okay? So let's go ahead and go back to our code editor, and let's take a look at what I mean by that. So I'll define my own pi. This is not something that you should do, right? But I'm going to go ahead and define my own pi here for demonstration purposes. I is equal to 3.14159. I won't get any more accurate than that because I want to play around with this. Okay? Now, if I just print out that pi is equal to %f and the line, what is this going to print? It's going to print that value out, but to 6 decimals of accuracy. I only specified 5 decimals of accuracy, so what's the 6th decimal of accuracy? 0. It's not truncation. We're not dealing with the integers here. And it's not necessarily garbage. If I went out further, past the 17 digits of accuracy that it has to store, it might end up being garbage. But this is just undefined, so, well, 0, right? Now, how can I print more decimals of accuracy. Let me go ahead and add, like what I was saying, the modifier to this. I will put a period and then a number. How many decimals of accuracy do you want? In this case, I want 10. Right? So let's go ahead and compile this and see it print out that it's going to print out 10 decimals of accuracy. But of course, the rest of them are just zeros. Right? If I specified 5 decimals in my declaration and I wanted 10 printed, then it's printing out 5 zeros after that. Right? What if I wanted 20 decimals of accuracy? Now here's where you get into the garbage, right? Because there are only 17 digits of accuracy, and so when I try to go out that far, then it starts failing, right? And it'll give you 20 decimals of accuracy because that's what you asked for, but it's garbage. Right? Yeah, go ahead.
That only says 3.14158.
Yep, it's garbage, right? Garbage is it's going to be less accurate the further that you go out, and it'll affect other things, right?
Even though you specifically defined 3.14159.
Yep, because the garbage infects the rest of it, right? For all now, I mean that's not that far off. If I went only out to say, I don't know, 15, that's safe. I'm sure that it will maintain the zeros then, but the second that you get out to garbage land, now everything is garbage land, right? Just like if I were to start with garbage and I add 5, what is garbage plus 5? 1. Garbage plus 5 is?
Garbage.
Still garbage, right? Garbage plus anything is garbage. And so we've got that. Yeah,
Garbage plus infinity. Is it infinity or garbage?
garbage. Yeah. I don't think that you can. Yeah, it might be infinity. I don't know, but you'd have to test that out. A question online is: will there be integral promotion for variables int to double? Yes. So what they were asking was earlier in the lecture. What if I've got int x is equal to 20? Int y, or let's go with double y is equal to 10.5, double z is equal to x plus y. Oops, plus y. What value will be stored in 20 or in z at that point? 30.5. Why? Because that 20 magically becomes 20.0 for the purposes of that addition. Right? The only time that you have to worry about that is when you've got integers. Integers divide, and even then, the only time you have to worry about that is integers divided by integers. Right? Good question online. Keep them up. All right. More placeholder stuff. Okay. Let's do one more here first. What if I wanted fewer significant figures? What if I only wanted, say, 3 digits of accuracy? Well, 3 digits of accuracy would be 3.141. It ends up being 2. What could we infer that it did to us? That the 3.1415, what happened? Not garbage, but it rounded it up for me. For the purposes of printing only. Let me show you, and I will print it again. Did it change pi? Nope. It will still be 3.14159, blah, 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 blah. Right? So it only changed it for the purpose of printing, not the actual variable. If you want to change the actual variable, you need to change it. Right? Let's suppose that I had a balance instead, double balance. Right? Equals $123.54.5. Right? This isn't merry old England. We don't have halfpennies. Right? Instead, we don't have. What should this be? 120. If you're don't lose that halfpenny, I guess. What's the bank going to give you? $123.54. Okay, you think that a bank would screw you and round down and steal your halfpenny. But let's go ahead and assume that it's a nice bank that is going to round that up and give that to you. Right? So let's be the nice bank. And how can we do that? let's go ahead and update our new balance. Double new balance. All right. I want to round that to the nearest cent. Well, if I RTM or RTFM, the actual the math library, I'll find that there is this nice round function there. I'll go ahead and round that balance. And let's print both of those out. Balance. And balance. And new balance. New balance. Recompile and run. Is it going to give me $123.55? No. It's a very generous bank. They rounded it all the way up to the next dollar. There's no bank like that. Right? So what can we infer about that round function in the math library? It rounds to the nearest full whole number, right? Oh, are we dead in the water? What I want it to look like is something like this. $123.54, which is a whole number. And then I can use the round function in the math library. What's the difference between this number and this number? 2 decimals, right? Moving that decimal over. What could I do to balance to move that decimal over? Multiply it by 100. Floating point number, double, and an integer. The result is going to be double. So I do not need 100.0, but it's okay if you put it there. All right, let's try that one more time. Super generous bank. Now they've given me over $12,000 for free. Right? After rounding. Bank error in your favor. There ain't no such bank error in your favor in real life. Right?
They are trying to kill you, John.
The only way you can get a mistake like that is by going to a disreputable web, stock trader and then exploiting some bug and then hoping that you get your money out before they catch you. Right? Yeah.
That, and if a bank ever does make a mistake, they will just send their agents in the middle of the dang night to correct your bank statements for you.
I'm sure that there would be some legal issues there. So how do we correct for that? We moved the decimal place so that we could round to the nearest whole number. Now we need to move the decimal place back. So if I multiplied by 100 to to move it to the right or whatever it was, yeah, move it to the right. What do I do to move it to the left? Yeah. All right, divide by 100. Floating point number, double, divided by an integer. Do we have an integer truncation issue here? Nope, because one of them is at least a double. But if you're worried about it, go ahead and put a 0.0, and you're good. Now let's see if our new balance is what we wanted. Yep, it rounded up to the nearest cent. Excellent. So when we get to functions, we'll learn that this is a basic tenet of using functions. Don't rewrite from scratch, right? If you can use a function off-the-shelf solution, you do so, like rounding, right? It would be pretty complex, like 5, 6, 10 lines of code to do your own rounding to the nearest whole number. But there's already a round function built for you in the math library. Use it. Except that it wasn't exactly what we wanted, right? It was, well, it's kind of what we wanted, but we wanted to actually round to the nearest hundredths place. All right? Adapt it, right? Move that decimal place over, then use it, then move it back, right? You didn't have to write your own from scratch. You had to adapt what was already there in the standard library, but at least you didn't have to start from nothing. Yeah? That's ultimately what you would do. You'd actually probably cast it to an integer so that you get rid of it entirely or something. Then you would take the difference, and then you'd check is that difference greater than 0.5, and then you would add 1. Otherwise, if it's not greater than 0.5, then you wouldn't do anything. That's why I'm saying it's too complicated. Forget that. I'm going to use the round and then just modify it a little bit, right? And then it's a whole different story for negative values too, because now you're rounding up, right? And it's a completely different story. So take that 10 lines of code and double it because for other corner cases. And there might be some corner cases that we're not even thinking about, like 0. 0 rounded is 0, right? So add some more code to that. Get rid of that headache and reuse what's there. Right? Now, this doesn't quite look right because we didn't put dollar signs in front of it. Dollar sign and dollar sign, right? Money, right? If it's money, you label it as such. Right? There we go. Except that we don't print money out to 6 decimal places, do we? Nope. So how can I print it only to 2 decimal places? 0.2 and 0.2 in front of the F. Between the percent and the F, that's where you put the modifier. And this will end up looking very, very nice. Right? Okay. I've got my new balance here. Double. Another balance. This is only for demonstration purposes. These are terrible variable names. Balance is an okay variable name. Pi is an okay variable name in the context of using pi to compute a radius or something like that. But even then, you would use the math library's pi. Right? $1,793,432.12. There we go. Let's go ahead and print out the balance and another balance. Right? But I'm going to do it by not putting anything in front of it. I'm just going to print these as if it were a ledger, right? A financial ledger. There we go. Does that look nice? Does it look formatted? I mean, both of them are out to 2 decimal places, but is that how we generally like to see tables? No, we like to see them aligned. How do we like to see them aligned? All the periods all lined up in the same column. Right? So we can add another modifier here. The other modifier that I'm going to say is print a minimum of 10 columns. 10 columns. So I've got 2 numbers here. The first number, the number to the left, is a minimum number of columns to print. The second number to the right of the decimal place is the number of digits after the decimal place to print. Let's see the effect that this has. Right. Now it's all aligned. Right? In fact, let me put in printf a bunch of empty lines just to offset it. There we go. There. $123.55. That period is aligned with the next period because I'm printing out a minimum of 10 columns. Let's understand what happened here. 1, 2, 3, 4, 5, 6, 7. 7 columns for the whole part. 8, an eighth one for the period. 9, 10. It printed out 10 columns, and it's not going to print out anymore because I said a minimum of 10 columns. That helps us understand how this got printed. 1, 2, 3 for the whole part, 4 for the period, the decimal, 4, 5, 6 for the other parts. I said print a minimum of 10 columns. So what did it do on this side? White space, how much white space? 1, 2, 3, 4. Because if there are 6 involved in the value, and I said print a minimum of 10, right? What does that leave over? 4 to print to the left, right? And it's just going to print spaces by default. If you want to get fancy, you can tell it to print zeros instead, or a bunch of other things. We're not going to get that far into it. There are a couple of dozen other placeholders. There are a bunch of other tricks that you can use with printf style formatting. This is enough to get you started. Right? 2 modifiers here. The minimum number of columns, the exact number of decimals of precision. Right? All right. I'll make sure that you have all of this in your notes. All right. So as a review, you can modify modify it to specify the number of digits to print. Percent, say 20.20f. You can modify it to print a minimum number of columns. Say percent 10.2f. Right? And here's the chunk of code. Right? There. With our remaining 5 minutes here, I'm going to give you a preview of what you're going to do in your lab. Well, I think what you you did in your lab. Yeah, you'll do in your lab tomorrow, where you're not reading interactive input anymore. So here's a really quick program, right? Int x, int y. Printf, enter a number, all right, integer. Right? And then we've prompted the user to enter this input. What do we use to scan it in? Scanf. And because it's an integer, we use what placeholder? %d, right? D, right? And we need to read it into x. Except what am I forgetting? That's magic for now. Ampersand. Right? Enter in another number, an integer. And we'll read in y. And then we'll print it out. Printf. You entered %d and %d on the line x and y. Right? So this program is interactive in that if I compile it and run it, it prompts me for an input. I sit there and mash my keyboard, right? Hit enter. It prompts me for another number. I sit there and mash my keyboard again. And just to prove to you it is actually different things, I'll mash my keyboard differently. There we go. All right. And we get different numbers successfully read in. Right? The vast majority of software is not written to interact with people. Right? The front-facing consumer software that most people think of as computing, that's the tip of the iceberg. Right? The apps and the games and the point-and-click kind of stuff, the graphical user interface stuff, that's an extremely small part of all computing. The vast majority of programs, 99% of software out there is written to interface with other software. That's the whole point of writing software, is to automate stuff. Right? And there's no point in automating stuff if you have to sit there and stare at the keyboard, stare at the screen, enter, 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 hit, mash your keyboard, mash your keyboard, mash your keyboard, go. What I want to do is I want to run this program and immediately provide those as command line arguments. 432, 65, there we go. Right? I don't want to have to sit there and prompt for input, enter, 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 enter. I just want to give the input all up front and let it run. Right? I want to automate that. So that's what we're going to look at first thing on Wednesday. Right? And in fact, that's the last thing of the module, is non-interactive input. You'll see the difference in your lab tomorrow when you enter in birthdays. Right? I think you have to. You're given a program to compute somebody's birthday, and you prompt for the month, prompt for the year, prompt for the day, or you can provide it as command line arguments, and it takes care of it for you right away. All right? We'll see that tomorrow. You'll see that tomorrow.